Russ here from the Reg team. Our next talk today comes from senior consultant and researcher, speaker, and blogger Gavin Klondike. Gavin's talk is titled Hacking with Skynet, How AI is Empowering Adversaries. At the end of the talk, a link will be displayed so that you can join in on a live Q&A session with Gavin. All you need to do is click the link and you'll be taken over to the live Q&A channel. So without further delay, Gavin, over to you.
Hello, CactusCon, and welcome to Hacking with Skynet, How AI is Empowering Adversaries. Now, before we get started, I want to share with you something that may be a little scary, but really hits on what we're going to be talking about today. Late last November, there was a top Iranian nuclear scientist that was assassinated by what some have called an AI-powered gun. Now, there's conflicting reports as to what exactly happened, but this isn't too far outside the realm of possibility. There's already tutorials online on how to create an autonomous sentry turret, and they'll use LiDAR for object detection. But what if we add a little bit more brains into the mix? What if we added in some facial recognition or deep learning object detection tracking like YOLO or You Only Look Once? Now we're starting to get somewhere. Anyways, that's your bottom line up front, what we're going to be talking about today, and why this presentation is called Hacking with Skynet. My name is Gavin. I am known online as GT Klondike. I am a security researcher, an AI Village officer, and a senior security consultant. I also run a passion project called NetSec Explain, where I explain advanced level computer and network security topics in an easy to understand way. So for the uninitiated, you've probably heard machine learning, artificial intelligence, and deep learning used interchangeably, but there's a difference, and we'll go over that. So artificial intelligence is a big umbrella term that covers not only machine learning, but other types of artificial intelligence, like rule-based artificial intelligence and traditional or classical object recognition. Underneath that umbrella, we have machine learning. Now, machine learning uses statistics and data to come to inferences or decisions based on the data. So the algorithms will stay the same, but the data is what allows the machine to make the decisions that it's making. And then as a subset of machine learning, we have deep learning. This is where we have deep neural networks. So think of this presentation as being really two smaller talks. So in the first section, we're going to be talking about offensive AI tools. What's out there, what's possible, and what exists today. And then in the second part, we're going to talk about adversarial machine learning. This is hacking or attacking machine learning algorithms and machine learning based software. So why is that important? Well, there's no question we've already seen the effects of machine learning in the security industry. We see how it can help us with log detection, anomaly detection, and sifting through massive amounts of data. It's very valuable, but there's another side to this coin. How is this allowing attackers to improve their own capabilities? So let's jump into it by talking about offensive AI tools. So why do we even want offensive AI tools? Well, what this is going to allow us to do is explore the target attack surface very quickly, especially in today's day and age where we have a lot of IoT devices. We have billions with a B lines of code on millions of devices stamped into a chip and sent across the world. I can't even wrap my head around the idea of billions of lines of code, let alone the potential vulnerabilities that could be associated with that. So how can we operate at a speed and scale that will allow us to handle this with our current workforce? And that's exactly what offensive tools will allow us to do. It'll allow us to automate some of the penetration testing and vulnerability assessments, but it also allows adversaries, the bad guys, to attack us in many different and unthought of ways. So this is going to allow us to move at a speed and scale that we have not been able to do before. And it's going to allow us to automate our manual analysis. Plus, the added caveat, where we're going to be able to uncover some hidden blind spots in our defensive tools and software, and so can they. So how realistic is this? Well, in 2016, DARPA initiated the Cyber Grand Challenge, where it pitted teams of researchers against each other in a fully AI or autonomous capture the flag challenge. So as part of this challenge, the AI, or the automated applications and systems that they built, had to perform its own vulnerability discovery, exploitation, post-exploitation or patching, and data theft. It would then take the exploits that it found in its own systems and launch them against other systems automatically. Everything was air-gapped, and the only humans on that side of the fence were the referees. So it was absolutely crazy, and if you haven't, I highly recommend that you check it out because some of the results were insane. For example, one of the researchers, or one of the AI units, actually found vulnerabilities in a challenge that the author didn't initially intend to have in there. But another one identified and patched that same vulnerability. So this really gave us a glimpse on the world stage of what AI can do and how it can be applied into the security sphere. So some applications of offensive AI. Unfortunately, I'm not going to be able to get into all of them, but I'm going to be doing a whirlwind tour to kind of show you what's out there and what advancements are being made today. So right now, applications of offensive AI, we have social engineering. We already know that we can use AI to perform defensive detection, but what if we're a malware researcher or a malware engineer and we want to identify whether or not something is in a sandbox? So how can we find ways to bypass intrusion detection systems and even antivirus systems and evade those or shut down if we detect that we're located on one of them? We can use, or adversaries can use, artificial intelligence in order to evaluate data leaks. So massive password dumps or credential dumps in order to see who's connected to what and how things are related. Automated network exploitation, both internal network exploitation and external network exploitation, and then automated software exploitation. So this will take fuzzing to a whole new level, develop new and interesting exploits and proof of concepts. So let's start off talking about social engineering and applications for that. So the first one I want to bring up is StyleGAN. StyleGAN is a project by NVIDIA, and what it allows us to do is create AI-generated human faces that look realistic. So how do we apply this to social engineering? Social engineering, usually what you'll have is a persona. And so this will be for the social engineering pen tests, and this will be for red teams. You'll develop a persona, somebody that seems plausible. Usually this comes with a name and a face. Traditionally, what people would do is they'll go to the 10th page of Google, or they'll look up a stock photo, grab that, and post that as a profile picture. And so I, as a 32-year-old male, can impersonate Becky, a 20-something female who's looking at getting started in the industry. And then I can perform my social engineering tasks from there. I can send emails to everybody in HR, accounting, sales, whatever, in order to gather more information from a company. But a clever security researcher or network defender will be able to see that image. If it doesn't pass the sniff test, they'll grab it, reverse image search, and they'll find that exact same person as, I don't know, Catherine in New York, as image that I had stolen. So things are going to match up and immediately flagged as false. But why steal somebody's identity when I can create a whole new identity? StyleGAN will let me generate a profile picture, and there's other tools out there that will let me generate social media content, long-form blog posts, and even my own voice. Now, before I show you the voice part, I kind of want to show you some interesting things about the way that StyleGAN is generated and some things that you can use to identify and see if somebody has already done this. So if you notice that all of the images, they're all looking straight. Another thing that you might notice, and this isn't true for all images, but you'll see artifacts happening in the background. The background's really blurry, but if you see things that are supposed to be vertical or in a straight line, like trees or fence posts, you can kind of see some distortion or artifacts. An easier way to demonstrate this is with AI-generated cats. So all of the images here are also generated by StyleGAN of cat pictures. And you can see the level of detail that they have in the fur and the whiskers, but artifacts do happen. Their paws aren't rendered properly, and you can even see some weird like WTF stuff going on over here. So let's talk about voice. What if it's not enough for me to communicate over chat and somebody wants to actually conduct an interview or get on the phone with me? How can I impersonate Becky? Well, I can use a friend of mine, or I can use a synthetic voice that'll be able to put in the right suggestions that I need in order to ask the questions of part of my social engineering campaign and get those trophies. So I'm going to show you a couple voice clips from Lyrebird and Tacotron. Lyrebird is a real organization, and it's pitched as a reverse transcription service. So you type in whatever it is you want to say, and then you send it off to Lyrebird, and they will give you a human synthesized voice saying those things. And then Tacotron is a Google project that does a similar thing. So let's go ahead, check out the original voice. And these first two are from Lyrebird.
In another moment, down went Alice after it. Never once did she consider how in the world she was to get out again.
Awesome. And so the synthetic voice based off of that sample image, or that sample clip. Oops.
My voice might be generated by a computer, but I think it sounds pretty human. I don't know exactly how they made it, but I'm really impressed.
Ooh, very nice. So what we can do is type up a script or type up a series of scripts, and we'll react to question and answer segments and then use that for social engineering. But you notice that it sounds a little synthetic, or it just sounds a little off. You can explain that away as saying it's just part of a bad connection, or I'm using Wi-Fi calling or something of that nature. So the last one that I want to show you here is Tacotron. And there's been a lot of advancements since I originally pulled this audio clip. But this one, what I want you to do is while you're listening to it, listen to the breaths and spaces. Normally in human speech, we'll have, where there's a comma or a period, a breath or a space, something that kind of fills in that gap. Another thing, and this isn't part of this research, is they'll introduce filler words like and so and. So anyways, take a listen to this clip, listen for the breaths.
Only the photograph really showed how much time had passed. 10 years ago, there had been lots of pictures of what looked like a large pink beach ball wearing different colored bonnets. But Dudley Dursley was no longer a baby, and now the photograph showed a large blonde boy riding his first bicycle. On a carousel at the fair, playing a computer game with his father, being hugged and kissed by his mother.
Ooh. And these are technologies that are advancing all the time. So soon, we might have to keep an eye out for synthetically generated voice that is trying to social engineer our organizations or us as individuals. So let's move on. Next, we have sandbox detection. So for malware, if you're a malware engineer, what you want to do is try and avoid sandbox detection as long as possible. And the reason is because antivirus companies such as Norton, Kaspersky, McAfee, what have you, they try and grab malware samples or potential malware samples. They throw them in a special environment, and then they just let them run and see what they do. So as a malware engineer, I want my malware to go undetected for as long as possible, which means that I need to find a way to get past this sandbox or this phase of analysis that they perform. So I'm going to perform sandbox detection and implement that into my malware. So the way that sandbox detection, some of the researchers over at Silent Break Security, what they did was they identified what is something that will identify, or what are some processes that we'll see inside of legitimate operating system that is being used by a user, and processes that are just in there by default on some of the well-known sandboxes like FireEye and Cuckoo. What they were able to do is use process lists, user count, and other types of information on the host operating system as data points. And they said, based on those data points that we've identified, we're going to set a threshold, and based on that threshold, we're going to determine whether or not we're in a sandbox or on a legitimate user system. If we're on a legitimate user system, go ahead, execute, no problem. If we have identified that we're on a sandbox, then shut down, delete itself, and it can't be analyzed. So for this, every AI or machine learning algorithm, you need to set a threshold. So it gives you a certain confidence level based on the data points that you give, and then you set a certain threshold. So in this case, we have hosts A, C, and F that were determined to be part of a sandbox. And that's because they didn't reach this threshold of 168, which is the host average score. So if you didn't reach the host average score, then I'm going to consider you a sandbox and just shut down. So the next part that I want to talk about is automatic network exploitation. And these are some tools that were released a couple of years ago that are still being updated today, Deep Exploit and Goithon. They work very similar, but they automate the network penetration testing process. So where they'll start is they'll begin with an Nmap scan or a series of analyzers. So maybe a Nessus scan or OpenVAS or something of that nature. And then they'll follow it up with identifying certain ports. So if port 80 is open or 443, then we're going to perform web crawling using Scrappy. Based on the information that we pulled from the Nmap scan, Nessus, and Scrappy, we're going to be able to identify and enumerate the type of service that's running on the system. So are they running Apache, Nginx? Are they running JBoss? Are they running Jenkins? Things like that. Then they're going to port it over to Metasploit and see what existing Metasploit modules there are and try and kick off the types of Metasploit modules that'll target that specific type of system. They'll run through the gamut, see what connects back, and then they'll be able to print out a nice report that'll tell you what was exploitable, what was found, and what was actually exploited. My favorite one in the network intrusion or the network penetration testing section is this application called Death Star. Now, Death Star is one of my favorites just because of the way that it works. It seems like it's just a bunch of if statements, but it's a lot more complicated than that. So here we start off saying, going from a regular domain user account to try and escalate up to domain admin. And we already see attack graphs like this kind of being generated by tools like Bloodhound. But this one's a little unique. So it starts off in a start state and it says, okay, do I already have domain admin credentials or do I already have a domain admin user? It goes down one track if we have the user, it goes down another track if we have the user and the credentials, and then it ends. If not, then we're just going to go ahead and start the next loop. And we go down this middle spine column, if you will. So it says, okay, let's spawn a new agent. Now, do we know where the domain controllers are? Yes. All right, let's enumerate the domain controllers. So we're going to use get net domain controller, get net group member, invoke user hunter, and try and identify all of the paths that we can to get to a domain admin. Now, I should have said this earlier, but this is built on PowerShell Empire 3. And so some of these things may work, may not work. I know PowerShell Empire kind of has some criticisms against it, but besides that, the idea is still there. Eventually it'll go down, it'll find domain admin or it'll find a new Windows system and it'll say, hey, let's enumerate the processes on the system and then let's identify the operating system. Are we running Windows 7? Yeah, let's run Mimikatz on it. Are we running Windows 8, Windows 10? Let's try other exploitation techniques. And then if there's other users on the system that we don't already have in our list, let's add it to our list and try the whole process again. So this is very cool, and I'm excited to see where this will go. But we might see some adversaries or even APTs start to use this kind of automation in some of their tools in order to traverse through the network secretly and quickly. So be on the lookout. Anyways, that's all I have for the offensive AI tools portion. But I don't want to leave you empty-handed on here. If you want to develop your own offensive AI tools, here's my recommendations. First, start with a pipeline. So something that is repeatable and automated or rote. So for example, you'll start with an Nmap scan. Okay, cool. With an Nmap scan, what can we do with this? Oh, well, I see port 80 or 443. Let me go ahead and perform some analysis on that. We saw with Goithon and Deep Exploit that they're using Scrappy. And so we can also use GoBuster, Dirbuster, something of that nature, and then we can enumerate all the different directories. We can use Aquatone to grab screenshots. So now we have a lot of information about this potential web application. We can continue further down our analysis. We can try identify a login page, try and log in as a potential user or as a using a password list. And so this is the way that you develop the framework for building AI tools. You just take a process that you do repeatedly, build a pipeline out of it, and then turn that into data to be passed on to the next process or the next pipeline. So the next thing that I want to talk about is adversarial machine learning. Adversarial machine learning is actually attacking the AI algorithms. And this is specifically machine learning. So there are really four primary ways to attack a machine learning model. First is to look at the model robustness, which isn't really attacking the model itself so much as attacking the software around the model. All of machine learning, as advanced as it may sound, is just software and is vulnerable to the exact same software vulnerabilities that we see day in and day out. The three others, we have model evasion. So how can we develop some sort of adversarial example that'll bypass the model? So if the model has intrusion detection or something of that nature, how can we actually use the intrusion detection built into that model to bypass it and be considered benign? Model poisoning is how do we actually influence the way that the model learns in order to build new adversarial examples without being detected, or to just completely tear down the model and ruin it. And then we have data leakage. So maybe we have access to the model in some way, shape, or form, and then we can ask it targeted questions in order to leak data and information that the model was trained on. So this can be really dangerous for top secret information or HIPAA information, right? PHI data. So if a model is trained on PHI data and it's vulnerable to data leakage, then we as adversaries can just extract that PHI data out of the model. It's very hard to do, but definitely a thing. So the first thing I want to talk about is model robustness. And sometimes the software is just broken. If it's not a robust model, it's not a good model. And that is true, absolutely true for machine learning. So a really good example would be self-driving cars. Self-driving cars, you'll see all these cool hacks that are happening. Security researcher will find them. They'll submit them off to Toyota or Jeep or whatever company. And then the company will come back and say, oh, that's not a security problem. Why not? What happened? Like, I was able to influence your self-driving car. Well, this is where we talk about model robustness. The model needs to be able to exist in its environment without having problems. That's way before we get to the security section, where the model can exist in its environment, but we as adversaries can try and influence it or attack it and make it to do something that it wasn't expecting to do. So in this example, actually, one of my favorite examples is called the summoning circle attack, where somebody can just paint what seem like road lines out of salt onto a road or concrete or asphalt. And as soon as the self-driving car goes into it, it gets stuck because it knows that it's not legally allowed to cross that intersection or that street, but it also can't back up. It can't go off to the side. So it gets very confused and it has no idea what it's supposed to do. Another example of failed model robustness with self-driving cars is a team of researchers working on Tesla was actually able to get a Tesla car to switch lanes into potentially oncoming traffic. Now, the reason why this isn't really a security concern is because what they were able to do is just put little LiDAR stickers on the asphalt. And so they just did the Wile E. Coyote version of drawing lane lines over into the oncoming traffic. So not really a security concern, more they just need to work on their model for their self-driving car. Let's move on. So this is where we start getting into the actual adversarial approach. right? So when you're going to attack, or when somebody is going to attack a machine learning model, you have either a white box or a black box. The white box is fairly self-explanatory. White box here, we have the source code or the data that the model was originally trained on. We have the way that the model was created. And so we can just do a code review and we can rebuild the model, and we can try and find little points in that model that are vulnerable. The black box model is a little bit more complicated. Instead of trying to attack it like a web application from a black box perspective, what we try to do is ask the model a series of questions, right? Millions and millions of questions, so that we can get as many data points as we can to train our own surrogate model. Now, if you're familiar with cryptography and some of the crypto games that are done there, we can use that surrogate model to act as an oracle, where we can try and attack the oracle, and whatever works on the oracle should work on the original model. This is because of a phenomenon known as attack transferability. The phenomenon that's been identified is if an attack works on one specific model, then it'll work on many other types of models. It doesn't even have to be made with the same algorithm or the same data. It's the same type of features that really kind of messes with the model. And we'll see why this is important a little later on. So before we can begin attacking an AI model, or a machine learning model, first we need to understand what is a realistic attack surface. Now, I'm sure that you've seen an image of a panda. You manipulate some pixels and then it identifies it as a bird. That's not really realistic, because the only way that you can attack that panda image and modify the pixels is if you have some sort of physical access to the model itself. And at that point, why modify pixels in a really convoluted way when you can just change them so it is a picture of a bird? It's a little weird. So here's the generic machine learning model and the process that it goes through. And then as an example, so that it makes a lot more sense to those who aren't familiar with machine learning, I have a network intrusion detection system built on machine learning to kind of illustrate what different points, what means what at different points. So here we have a physical object, which is the observed event. So this could be a road sign. This could be an image of a road sign, I should say. This should be distance to an object. In our network intrusion detection system, we have the attack traffic itself. Then what we're going to do is digitize that information, and we're going to transform it into something that the model can use. So we're going to take that image, we're going to transform it into bytes, or we're going to take that attack traffic and we're going to transform it into a PCAP using TCP dump or Tshark or something of that nature. And then we can take that, pull the features out of it, and put it into our machine learning model. Now, our machine learning model is kind of a box in and of itself. It takes input features and it provides an output. So that output is always going to be some sort of score or some sort of scale. And so in this case, we're going to have our packet metadata, and then it's going to output our attack probability. What is the probability that what we're looking at right now is a network attack? And then at that point, it goes on to the rest of the software that makes a decision. It says, okay, if you reach this threshold, anything above it is attack traffic, anything below it is benign. And that's just a binary classifier, a 1 or a 2. There are many other types of classifiers. For example, object detection. I know ImageNet can detect, I believe it's 200 different types of images. Is it a dog? Is it a cat? Is it a plane? Is it a train? That's all based on this decision piece. So let's see how this works in practice. First, we're going to talk about model evasion. In model evasion, or I should explain this diagram first. We have a massive amount of theoretical space. This is all the possible objects in the world, but we can't look at all the possible objects in the world. So what we do is we collect as much data as we can, and this is our training and testing data. So we have all of the data that we have. It's clean, it's labeled, it's clear. And so we split it up. Usually it's 80-20 or 70-30, where the model is trained on 80 or 70% of the data, and then it's tested on that 20 or 30% that's left over. So the reason we do this is the same reason, the same way actually that we teach students in elementary school, right? We teach them as much as we can on different mathematical principles, and we use many different examples of what math looks like, and then we test them to see if they actually understand what's going on. So here's where we get into our adversarial space. Adversarial space is where we as attackers are actually able to try and hide and blend in. So this is outside of their training and testing data, but we need to have some sort of knowledge of what they used in order to perform some sort of malicious action. So for model evasion, our adversarial space is also kind of technically part of our testing space, where we try to hide in the blind spots. So we try and make the things that it's looking at as benign, but the things that it's not looking at as malicious that'll get through. So a perfect example of this would be naive Bayesian spam filter. And if you want more information on how spam filter like this works, or how the machine learning process works, take a look at my workshop that's going on later today. So how do we defeat naive Bayesian spam filter, just any regular machine learning spam filter? Well, here we have an email that it flags on certain keywords. So the probability of a regular email having the word Viagra is pretty low, but the probability that a spam email has Viagra is pretty high. And so it looks at all the words, it scores all of those words and says, okay, here's a bundle of potentially bad words, here's a bundle of potentially good words. If we add them all together, then we can see where we fit on this little scale. So in this case, here's an email that the spam filter is 99% sure is spam. So it throws it out. How can we evade it? Well, one clever way of doing this is looking at the way that emails are constructed. Emails are typically HTML files. Now, a typical spam filter, or a regular spam filter, and this is exactly what they used to use back in the day, only looks at the keywords. It can't determine whether or not it's a word that's being shown to the user. So what we can do is go to Wikipedia, grab the entire article for a horse, and put that in as a HTML comment. So to the user's perspective, it doesn't see any difference in the spam email or in the regular email. But from a machine learning perspective, it takes all of the words from that Wikipedia article into account, and it says, hey, you have a lot more good boy points than bad boy points. You get to go right on through. So that's an example of model evasion in action. Let's see what more we can do with it. So the researchers over at Skylight Saber actually did something very similar with the Cylance antivirus. In this wonderful article I highly recommend checking out, called Cylance, I Kill You, where what they were able to do is identify different features that the Cylance antivirus was able to look at and perform on. They did a little bit of reverse engineering, and they found that there are certain applications that are whitelisted inside of Cylance. So in this case, they looked at online video games. So online video games, they found certain things were whitelisted, so they just grabbed as many as they could and put those into their antivirus, or into their malware samples. So here we can see the score before making the change and the scores after making the change. So the one that entertains me the most is actually the Zeus malware, where it is at -997, one of the worst malware that it was able to identify. And then after padding it with a whole bunch of good boy points, it now became 997 positive, which is one of the best examples that Cylance was able to identify. So now that they're actually able to disclose what game it was, it actually turns out it was Rocket League. So they took words or features sets from Rocket League and put them into their malware samples. But they also tried other games like Fortnite and League of Legends. So how do we prevent model evasion? Well, there's a few different ways. What we can do is actually perform adversarial training. So the idea is that we know we're going to come across people who are going to try and manipulate our model. So what if we put those kinds of manipulations in our training set so that we can identify them? This kind of runs on the same principle as what is called chaos engineering or engineering chaos, which is, hey, we know that we have a network, our servers are going to go down at some point, or something's going to happen. Hard drive's going to die, power's going to go out. How do we account for that? So engineering chaos, what they'll do is they'll have a CISO or somebody of that nature walk into the data center and just start unplugging servers, right? We know that there's going to be an outage at some point. How do we handle that? How do we protect against it? So if you go in, start unplugging servers, then what you're going to do is start to develop processes and policies around those potential outages. So it's not a matter of if, it's a matter of when, and you know what types of things are going to happen. So you begin to train your model on adversarial examples, or you begin to train your data center or your processes on malicious insider or power outages and other unexpected things. Another way to prevent model evasion is what's called defensive distillation. So defensive distillation is just really a fancy term of smoothing a curve. So in this case, instead of the model looking at the email, right, the email example that we had, instead of it looking at the email and saying, okay, there's a bunch of bad boy points, oh, here's a bunch of good boy points, and it goes straight down, what it does is it smooths the curve so it can't do a radical change. So that isn't entirely foolproof, but it definitely helps make the model a lot more resilient against adversarial examples. And then the last one is called monotonic classification. Monotonic, also another fancy term for the graph only grows in one direction. So in this case, we see a non-monotonic example where it'll dip down below the decision boundary. It'll dip back up as soon as it sees all of the words in the article for a horse. And then in the monotonic example, we see that it only goes in one direction. It starts accumulating bad boy points, and once it hits a certain threshold, it doesn't matter what you do, Jesus won't save you, you're bad. So those are some evasion defenses. Next, we have model poisoning. This is where an adversary is actually able to influence the model itself. Now, this is really unique because it almost exclusively works on what are called online learners. Machine learning models stop learning as soon as they're done being trained. To work on that, engineers have developed online models where they will classify images or data points, data objects, as benign, malicious, or whatever different classes they have, and then they'll use the data from the stuff that it had classified to retrain itself. So a really good example of this would be network intrusion detection, where it needs to learn how your network operates, what is baseline, what is stuff that's normally seen. So for example, in company A, telnet might be something normal. It's probably something the security team doesn't like and they want to get rid of, but for the time being, it's normal. But in company B, telnet traffic is immediately a red flag because it's all clear text. So for an online learner, what we want to do is add adversarial examples into the adversarial space and then move that information into the training space so that the model is slowly moving the line to what is acceptable. So a couple examples of model poisoning would be the Microsoft Tay AI. Tay AI, if you're not familiar, was a Microsoft Twitter chatbot. And I use was because people over at 4chan decided that they wanted to try and take it down. Tay AI was pitched as a Twitter bot that will learn from conversations that it has with people, and it becomes more intelligent over time. So the people over at 4chan were trying to decide, what's the worst that we can do? It took only about 16 hours before Microsoft permanently shut it down, which is terrifying because imagine how many engineers, how many software developers were behind this in order to develop the system that is now just permanently shut down. So the way they were able to do that was just treat it with some conversation pieces, and it would learn over time what was acceptable and what was not. So it only took about 16 hours before it started saying things like Hitler did nothing wrong or other racial slurs. Another form is Jacobian Map Saliency Attack, or JMSA. And this is where we kind of modify certain pixels. So it's very technical and academic and not something that I would really consider realistic in a real world setting, but definitely something to be aware of. So in this example, we have a 70 kilometer per hour sign, change some pixels, and then it drops down to 30 kilometers per hour. So we may be able to influence a self-driving car by being able to change some of this stuff. But remember what I said, it's almost exclusively for online learners, and self-driving cars don't really do online learning that much. So just some examples to be aware of. So how do we prevent model poisoning? Well, there's a few different ways. We can train the model for longer periods of time, or have longer periods of time between the trainings. So what that'll do is allow the model to accumulate a lot more examples that it can be used to train the next version of that model. So it makes it a lot harder for the adversaries to influence enough of the data for it to be statistically significant. Another way that we can do is analyzing longer periods of data. It's kind of the same thing. And then we can just minimize the impact of adversarial training examples by incorporating our own adversarial training examples, or limiting what the adversaries are able to get through, or what data points that the model collected, how many of those actually go into retraining the model. So the last one we have here is data leakage. Data leakage, I mentioned earlier, can be really devastating if you're creating a top secret model, or if you're creating a model that is built on personal healthcare data, or PHI or HIPAA compliant data, also privacy, especially if you're concerned with GDPR. So the idea here is models being trained, if they are what's called overfit, will store some of the information, or it'll memorize some of the information. So in this example, the headlines were saying, oh my God, this Google AI, it memorized the test, and so it was able to cheat. That's not really true. This is a really well-known phenomenon called overfitting. Overfitting is just the AI model memorizes certain things instead of generalizing. So if 2 plus 2 is 2, or if 2 plus 2 is 4 every single time, and then you say, okay, well, what's 8 plus 5, it'll say 4, because it only memorized certain answers. It's a really poorly performing model and part of a whole nother problem. But overfit models do go into production sometimes. So usually we'll see this when models are too good to be true, because it's memorized the answers that it needs to memorize, which means that it'll usually perform really badly when it's given a question that it hasn't seen before. It can leak private or proprietary data, and then it could also allow model theft by competitors, as I was saying with the black box testing paradigm, where you take a model, you ask it a series of questions, and then you create your own surrogate model. It's not technically stealing, but it's a nearly identical model, and so that's stolen proprietary data. So one more thing I want to leave you with is a conversation around adversarial stickers. So adversarial stickers, they look like melted crayons, in my opinion, but they were all the rage, especially when some of this research first came out, where headlines really grabbed on to the idea of putting adversarial stickers next to things. Maybe you can put something on a stop sign and it looks like a yield sign, or a crosswalk, or a speed up to 100 miles an hour sign. That's not really the case. So adversarial stickers, they look cool, but they suffer from a very critical problem. And that problem is attack transferability. They're not transferable. So if you had two models that operated nearly identically, right? So in this case, we have an image classifier that can identify bananas and other images. You can have one model that you create an adversarial sticker for, put it next to a banana, it thinks it's a toaster. The other model, if you use that same adversarial sticker, it may not pick it up. It may not consider that a toaster. It may still consider it a banana with a really weird thing next to it. So adversarial stickers, they look cool, but not realistic in a lot of ways. If you want more information on this, I highly recommend checking out the DEF CON 2018 talk by Sven. It's 30 minutes. He talks about adversarial stickers and the problems with them. And then I also recommend DEF CON 2019 by Rich Harang, talking about defeating facial recognition algorithms. So both of them kind of talk about this attack transferability problem and why, even though it looks cool, it's not realistic. So to recap, how has AI empowered adversaries? Or how will advancements in AI empower adversaries? Well, it's going to let them operate at the same speed and scale as machines. So now we're going to have AI defense tools against AI attack tools at some point in the near future. And this is also the very beginning of what AI can bring. So you remember back to the 80s and 90s where antivirus systems, intrusion detections, they were all basic scripts or very large, but still basic scripts. And now they've both turned into multi-billion-dollar industries. So I see AI and security being able to do the same thing for both the attackers and the defenders. And I think that we're on the very edge of where this transition will start. We're also already starting to see some of these adversarial attacks against real-world models. For example, the self-driving cars that I showed earlier, those are real-world models that researchers were able to get to kind of trap themselves. The adversarial sticker, that is a real model, but it's not something that can work in the real world against other models because of attack transferability. We saw silence, how silence could be bypassed. We saw how spam filters could be bypassed. So a lot of this is what we're starting to see with researchers, and some of these are what we're starting to see in the wild. Anyways, that's all I have for you guys today. If you didn't have a chance to ask questions in the Discord server, here's my contact information. If you think of something later on, go ahead, reach out to me. And of course, check out my YouTube video, NetSec Explained. And my slides are up on slideshare.net. So the slides, unfortunately, I wasn't able to cover everything, but of the things that I wasn't able to cover, I have up there on the slides. And of course, you can reach out to me and we can talk about them. Anyways, thank you for your time and attention, and have a good day.